Download this code from codegive.com, link in the description below. OK, let's dive deep into Shenandoah, a cutting-edge garbage collector designed for low pause time applications in Java. This comprehensive guide will cover its architecture, key concepts, configuration, and practical code examples to help you understand and utilize it effectively. Introduction to Shenandoah GC. Shenandoah is a concurrent, generational, region-based garbage collector for the hotspot JVM. It's designed to significantly reduce pause times, often targeting pauses measured in milliseconds, even with large heaps. It achieves this by performing most of its garbage collection work concurrently with the application threads. Key goals of Shenandoah **** low pause times * minimize the time the application is paused for GC, aiming for sub-millisecond or low-millisecond pauses. Concurrency * perform as much GC work as possible concurrently with the application, avoiding long stop-the-world pauses. Scalability * handle large heaps, hundreds of gigabytes or even terabytes, efficiently. Generational * like many other modern GCS, Shenandoah leverages the generational hypothesis: most objects die young. Why use Shenandoah? Shenandoah is a good choice when low latency is critical. Applications where long GC pauses are unacceptable, example real-time systems, interactive applications, financial trading platforms. Large heap sizes * when your application requires a very large heap, and traditional GCS, like CMS or even G1, struggle to keep pause times low. You're willing to accept a potential throughput trade-off. Shenandoah's focus on low pauses can sometimes come at the cost of slightly lower overall throughput compared to throughput-optimized GCS like parallel GC. 2. Shenandoah architecture and key concepts. Shenandoah's architecture is quite sophisticated, but we can break it down into its essential components. Regions * the heap is divided into a set of equal-sized regions. Unlike G1, which also uses regions, Shenandoah does not have the concept of young and old generations at the region level. Any region can contain objects of any age. This simplified region management is a key enabler for concurrency. Concurrent marking * Shenandoah uses a marking phase to identify live objects. This marking is done concurrently with application threads, using a snapshot at the beginning, SATB, algorithm. This algorithm ensures that any object that was live at the beginning of the marking cycle will be considered live, even if it is modified during the marking process. Concurrent compaction, evacuation. This is where Shenandoah truly shines. Instead of compacting the entire heap, Shenandoah evacuates individual regions concurrently. This means that it copies live objects out of a region while the application continues to run. This greatly reduces pause times. Brooks pointers, load barriers. To facilitate concurrent evacuation, Shenandoah uses Brooks pointers. A Brooks pointer is an extra word stored in each object's header, containing the forwarding address. When an object is moved, during evacuation, its Brooks pointer is updated to point to the new location. All loads from objects go through a load barrier that checks the Brooks pointer and follows it if the object has moved. This is the heart of Shenandoah's concurrent evacuation and requires careful engineering to minimize the performance impact. Write barriers * Shenandoah uses write barriers to track modifications to object references during the concurrent phases. This is necessary to ensure that the garbage collector can accurately identify live objects and perform evacuation safely. Ephemeral regions, humongous objects. Although Shenandoah doesn't have generational regions in the same way as some other GCS, it does have special handling for humongous objects, objects that are larger than half a region. These objects are allocated directly into dedicated humongous regions and are handled separately by the GC. Concurrent reset. Resets are done concurrently and involves operations that help in the next GC cycle. 3. Shenandoah GC phases. Here's a breakdown of the main phases in a Shenandoah GC cycle. 1. Initial mark, STW. A short stop the world pause to initialize the marking process. The root set, objects directly reachable from application threads, static fields, etc., is scanned. 2. Concurrent marking. Traverses the object graph, marking live objects. This is done concurrently with the application. 3. Concurrent cleaning. A process where the collector uses write barriers to locate objects that may be eligible for collection. 4. Final mark, STW. A short stop the world pause to complete the marking process and finalize the root set. This involves rescanning roots and processing any references that were modified during the concurrent marking phase. 5. Concurrent evacuation, region selection and evacuation. Selects regions to evacuate, copy live objects from. This is the heart of Shenandoah's concurrency. Live objects are copied to new regions. 6. Concurrent update. Reference * updates the object references to new locations in a concurrent way. 7. Initial update. Reference STW. Another STW operation to change pointers to new locations from the evacuated regions. 8. Concurrent commit. Commits the changes made during the evacuation phase, finalizing the memory updates. 9. Concurrent reset. Prepares the heap for the next GC cycle. 4. Configuration and JVM options. To enable and configure Shenandoah, you'll use JVM options. XX plus use Shenandoah GC * enables the Shenandoah garbage collector. This is the minimum you need to start using Shenandoah. XMX size and XMS size * set the maximum and initial heap size, respectively. Shenandoah works well with large heaps, so consider allocating enough memory. Example, XMX8G XMS8G, 8GB heap. XX Shenandoah GC heuristics equals strategy * chooses the evacuation heuristics for selecting the regions for garbage collection. Some common strategies. Adaptive, default, Shenandoah automatically adjusts its evacuation strategy based on the application's behavior. Static, uses a predefined strategy for region selection. Aggressive, tries to collect a larger number of regions per GC cycle. This might improve latency but could impact throughput. Pacing, an option that helps the collector to collect better and reduces the impact on performance. XX Shenandoah region size equals size * sets the size of each region in the heap. Larger regions may improve throughput but could increase pause times. The default is dynamically determined. XX Shenandoah initiating occupancy fraction equals percentage * controls when a GC cycle is initiated. This value, between 0 and 100, represents the percentage of the heap that must be occupied before a GC cycle starts. Lower values will trigger more frequent GC cycles, potentially reducing pause times but also impacting throughput. The default is 75%. Example, XX Shenandoah initiating occupancy fraction equals 60. XX plus Shenandoah print GC and XX plus Shenandoah print GC details * enable detailed GC logging to help you understand Shenandoah's behavior and tune its performance. These are essential for monitoring and debugging. XXCONCGC threads equals number * specifies the number of threads that Shenandoah will use for concurrent GC phases. Increasing this may improve performance, but it will also consume more CPU resources. XX plus use NUMA if your system has NUMA, non-uniform memory access, architecture. Enabling this option can improve performance by allocating memory closer to the CPUs that access it. Example JVM options V-code examples and benchmarking. Let's create a simple Java application that allocates a lot of memory and performs some operations. This will help us observe Shenandoah's behavior. We'll also demonstrate how to use a basic benchmark to compare its performance. Explanation *. 1 Shenandoah example class * this is our main class. 2 list underscore size and string underscore length * these constants define the size of the list we'll create and the length of the strings. 3 allocation loop * the for loop allocates a large number of strings and adds them to the data list. 4 do some work method * simulates some work by accessing and manipulating the strings in the list. This forces the GC to manage the allocated memory. 5 thread.sleep * keeps the application running for a minute after the allocation and processing are complete, allowing us to observe the GC's behavior. To run this example with Shenandoah * 1 save the code as Shenandoah example.java. 2 compile, javac Shenandoah example.java. 3 run. This will enable Shenandoah GC and print detailed GC logs to the console. Observe the output to see how Shenandoah is managing memory and the duration of the GC pauses. Benchmarking, basic example with JMH. To get a more accurate measure of Shenandoah's performance, you should use a proper benchmarking framework like JMH, Java Micro Benchmark Harness. Here's a very basic example. 1 add JMH dependency, Maven. 2 JMH benchmark class *. 3 run the benchmark *. Use the JMH runner to execute the benchmark. You'll need to configure the JVM options for Shenandoah, and possibly other GCS to compare against, in the JMH runner configuration. Important considerations for benchmarking * warm up * always allow JMH to warm up the benchmark for a sufficient number of iterations before measuring the actual performance. This helps to ensure that the JVM has optimized the code. Realistic workload * the benchmark should simulate a realistic workload that reflects the actual behavior of your application. Statistical significance * run the benchmark multiple times and analyze the results to ensure that they are statistically significant. Compare against other GCS * benchmark Shenandoah against other garbage collectors, example G1, ZGC, to determine which GC is the best fit for your application's needs. 6. Monitoring and tuning. GC logging as mentioned earlier, XX plus Shenandoah print GC details is invaluable for monitoring Shenandoah. Analyze the logs to understand the duration of GC pauses, the amount of memory collected, and the frequency of GC cycles. *jconsole/jvisualvm/visualvm*. These are GUI tools that can connect to your running Java application and provide real-time information about memory usage, GC activity, and other performance metrics. Java Mission Control, JMC, a more advanced profiling and monitoring tool that can provide even deeper insights into your application's behavior. JMC can give you detailed information about GC pauses, CPU usage, and other performance bottlenecks. GarbageCat GarbageCat is an open-source tool for analyzing verbose garbage collection logs. Tuning tips Adjust XX Shenandoah initiating occupancy fraction experiment with different values to find the optimal balance between pause times and throughput. Lower values may reduce pause times but increase GC frequency. Experiment with XX Shenandoah GC heuristics. Try different heuristics to see which one works best for your application. Increase XXCONCGC threads. If you have available CPU cores, increasing the number of concurrent GC threads might improve performance. Monitor heap usage. Keep an eye on the heap usage patterns of your application. If the heap is constantly full, you may need to increase the heap size or adjust the GC configuration. 7. Troubleshooting common issues. High CPU usage. If Shenandoah is consuming a large amount of CPU, it could indicate that the GC is working too hard. This could be due to a small heap size, a high allocation rate, or a poorly tuned GC configuration. Analyze the GC logs to identify the cause. Long GC pauses. Even though Shenandoah is designed for low pause times, it's still possible to experience occasional long pauses. This could be due to factors such as humongous object allocation or memory fragmentation. Examine the GC logs to identify the specific phases that are taking a long time. Memory leaks. Shenandoah can't magically fix memory leaks in your application. If your application is leaking memory, the heap will eventually fill up, and the GC will be forced to work harder. Use a memory profiler to identify and fix the memory leaks. Incompatible code. Shenandoah's use of Brooks pointers can potentially expose issues in code that performs unsafe operations on object memory, example using unsafe directly. 8. Shenandoah vs. Other GCS. Shenandoah vs G1. G1 is a general-purpose GC that aims for good throughput and reasonable pause times. Shenandoah is more focused on low pause times, even at the expense of some throughput. G1 has a generational region model, while Shenandoah has a non-generational region model. Shenandoah vs CMS. CMS is a deprecated GC that aimed for low pause times but suffered from fragmentation and other issues. Shenandoah is a more modern and efficient low pause time GC. Shenandoah vs ZGC. ZGC is another low pause time GC that also uses concurrent techniques. ZGC uses colored pointers rather than Brooks pointers, which has different performance trade-offs. Both Shenandoah and ZGC are excellent choices for low latency applications, and the best GC depends on the specific workload. 9. Conclusion. Shenandoah is a powerful garbage collector that can significantly reduce GC pause times, making it a good choice for latency-sensitive applications. However, it's important to understand its architecture, configuration options, and potential trade-offs. By carefully monitoring and tuning Shenandoah, you can achieve excellent performance and minimize the impact of GC pauses on your application. This tutorial provides a comprehensive overview of Shenandoah. To truly master it, you'll need to experiment with different configurations, monitor its behavior, and adapt it to the specific needs of your applications. Good luck! Remember to consult the official Shenandoah documentation and community resources for the latest information and best practices.